Here we are in Chapter 6, Discrete Probability Distributions. Once again, a lot of this can be done by the calculator. Clearly, we can do this freehand, and if you choose to take a college level class, you may be required to do so. But here at the high school level, if you have an understanding of what it is, and then we allow you to use the calculator to kind of give you what you need for specific questions. So clearly there's always ways to do things more in depth, and that's something that you would need to look into if you want to take this on a college level, where they have a probability and statistics course, usually 3 credits, that require for your major, no matter what it is. So we'll start with our first section here: probability rules, continuous and discrete random variables, histograms, which we talked about earlier, and then interpret mean and discrete random variables as expected values, and the variance and standard deviation. So by definition, a random variable is a numerical measure of the outcome from a probability experiment. Discrete has a finite or countable number of values, and we'll look at specific examples in a minute. And then continuous, something that has infinite many values: height, time, because you might give me one height and I can continue. If you say you're, say, 6 foot 2 inches, well, is it 2 inches, or is it 2.1 inches, is it 2.2? Like, it's very hard to measure that exactly. So examples like this, now normally you would not see the answers until I have this full screen, but since I don't have it, the number of light bulbs that burn out in a room of 10 light bulbs per year. Well, that's discrete. I can count how many light bulbs that actually burn out. The number of leaves on a randomly selected oak tree. You just count the number of leaves. The length of time between calls to 911. Well, it's very hard to measure time. Is it 2.1 seconds? Is it 2.11 seconds? Is it 2.112 seconds? Depending on the stopwatch, maybe every stopwatch could be programmed just a slight different. There's no two that are exactly the same, believe it or not. And that would be continuous. The number of goals in a soccer game. Well, that's discrete. You can clearly count the number of times the ball crossed the goal. A random variable is your choices. You should have answered A. Go back to a few slides, and there's your definition. Okay, a probability distribution provides the possible values of a random variable x and their corresponding probabilities. Very important. Look at this column on the right. If you add those numbers up, I'll give you, pause it, add them up, you'll notice something very unique. It equals to 1. So the probability random variable x equals, then it's a probability distribution if the probabilities sum equal 1, and there is no one probability greater than 1 or less than 0. You cannot have a negative probability in a probability distribution, or the sum cannot be greater than 1. And this is. None of these values, now these are just your x values, these are what your probabilities are. None of these are less than 0, and if you add them up, they do equal to 1. No, why not? Right here, that negative, no good. And then you can kind of go through them the rest. Now, what would be the answer for this? No, because number 1 is not allowed value for x. No, because the probabilities do not sum up 1. They do add to 1. No, because the probabilities are not in order. That doesn't matter. Yes, the probabilities are all positive and the sum is 1. This has nothing to do with it. I'm looking at the probabilities. Probability histogram, which the horizontal axis corresponds to the value of the random variable, and the vertical axis represents the probability of that value. So going back, these would be the x values, these would be the y values. And there you could see it. Probabilities over here on the left, x values on the bottom. the mean of a discrete variable. See, this is a nice fancy definition, and if you took the time maybe in a college class, you can write down every single one. But once again, watch how we can go through this. I have my TI-84. I go to my stat, I'm going to go into a list. I'm going to clear this list. Let me go up to the top here, to the L1, clear it, enter. Now I'm going to go back to this list right here, and I'm going to enter in those values. Let me see if I can move this over just so I can see it a little bit clearer. And now we're looking. Okay, so 0, 1, 2, 3, 4, and 5. I'm going to slide over to the second list and put the probabilities. Okay, now that I have both probabilities, the x values representing L1, L2 representing the y values, I can go to my stat, calculation, one variable stat. My list is in, my x values is the list. That's my x1. I had my frequencies or probabilities in L2. So I do second, number 2, which is L2, and I just enter and I want to calculate. And what do you notice? There's the 1.49, and there's the 1.49. So the mean is 1.49 given the probabilities of each of those x values specifically. So you can clearly see how they did it freehand. You can read as you're going through these, take the time, pause it, let you do an example. Okay, so the variance and standard deviation of that variable. Okay. Well, the standard deviation, if you look, is right here. Now, you won't have a sample because the sum is 1. That's why you won't have a sample. Okay? The L2 sum is 1. However, the standard deviation is 0.93. And if I square that number, see that? If I square the 0.93, I'm going to get the variance. So if I should be about 0.81, I just don't want to get off that screen. So if I square 0.9326, 0.9326, and I square it, there's my variance. Okay, there is my variance. I think I might have entered that incorrectly. And my data is still there. Yeah, 0.936, excuse me, 0.9326, and I square it. So my variance should be 0.8697. And that's how we would use the calculator for that. Okay, the probability in 6.2, probability, binomial probability experiment. We do this in Algebra 2. If you took my class, or even in pre-cal, if we get to statistics, we will also look at this. Here's some criteria. The experiment is performed a fixed number of times. Each repetition is called a trial. The trials are independent. Means you flip a coin one time, then you do it again. Whatever happened on the first time did not matter. For each trial, there are two mutually exclusive outcomes, success or failure. The probability of success is fixed on each trial of the experiment. N is the number of trials. Probability of success is 1 minus P. Is the probability of failure. So if the probability of success is 40%, well, clearly the probability of failure would be 60%. Now, once again, we can do this. If you go through these, just look at the slides. Now, here's the definition. You have a combination. Then you have times the probability to that power of number of successes, and then the minus the probability of failures and the subtraction of n and x. However, so here we are. We would have 20C5, 35. This would be 65% and 15. But once again, we can do this via the calculator. So if I put this right in here, just to kind of move it along, excuse me, let me bring this up, move this aside. Okay, so we're going to second, very important here, second vars. Second vars. All right, we're going to scroll down. There it is. Whoops, excuse me. Binomial PDF. Press enter. And here we are. Can't get any easier. And now these are all updated with the 2.55 face. So you should have the same screen that I have. Some of the older 2.43 operating systems did not allow that, but now we're ready to go. So we have the number of trials, 20. Now you can't have more successes than trials, so that should be your largest number. P, the percentage of success, 35%. And I'm using this module over here. X value, 5 have 3 or more cars, excuse me, exactly 5. Enter. And there it is, 0.172, 0.1272. So once again, let the calculator help. And if it was probability, cumulative, at least, go back to the slide, you would use second vars, binomial, second vars. I'm just going to go back up this way. CDF for either at least or at most. And once again, you can come here and see what you would need. So at least 3. You would need 3, 4, 5, 6. But how do you go to infinity? Well, think about it. If I want 3 or greater, you can always subtract. So let's go binomial. If I do 1 minus, remember the sum of all probabilities is 1. So if I do 1 minus second vars binomial CDF, we're going to use the same example, 20. Let me get back onto this one so I can remember what it was. 20. 0.35. Now, here's the thing. We'll do C here. In a random sample of 20 cars, what's the probability that at least 4 have 3 or more cars? So at least 4. That is 4, 5, 6, all the way up to 20. But I don't want to do this 4 plus 5 plus 6. I know whatever I get from 4 plus 5 plus 6 all the way to 20, if I subtract that from 1, that's going to be the probability of just 0, 1, 2, and 3. So I can do 3. And that's the probability of 4 to 20. And that's basically it for binomial PDF and CDF. You can play around with what you need for your specific. And histograms, you can play around with this. Very simple. Remember, once again, the X bars. And you can stop it at any point. Let me go back to your question bank, and then we're going to look at standard deviation. Once again, you know how to do that. Just look at your calculations. Now, the last thing in this unit, which I don't see on the PowerPoint here is poison distribution. So I'm going to bring this over here. You will have questions on poison distribution, okay? It follows a specific probability function, okay, where you're talking about a random variable, the probability of 2 or more successes in any sufficiently small subinterval, the probability of success is the same for any 2 intervals of equal length, and the number of successes in any interval is independent of the number of successes in any interval provided intervals are not overlapping. Now that's a bunch of things, but as long as they say it follows a Poisson distribution, there are some things you can find. So something like you would do this, once again, second vars. And if you see Poisson PDF right below the, okay? Now you have these letters. You have lambda, okay? So, for instance, we're going to use this as our mean. So let's just suppose our mean, type the value of u, was 10. The number of successes would be 4. And then you would get the probability of 0.01 or 1%. And that just says it's a 1% outcome that, in this case, let's just say the average of cars at a Wendy's drive-thru was 0.2 cars per minute between the hours of 11 and 1 a.m. on Saturday evening. You want to find a probability distribution for the random variable given that the mean is 0.2 and t is 30. So use this for Poisson if you need to look up and research more on Poisson. Poisson is really Poisson PDF. Go with it.